Module 4. Mapping Equipotential Lines. What is the phenomena? Electric potentials or voltages are represented through pictures to illustrate the electric fields. An equipotential line, as the name suggests, indicates the points of which these potentials are equal. Equipotential lines are always perpendicular to the electric field. Let the blue lines represent an electric field moving away from a positive point. Then the green line would represent a given equal potential. For parallel conducting plates, the electric field lines are perpendicular to the plates, and the equipotential lines are parallel to these plates. Movement along an equipotential surface would require no work because the movement is always perpendicular to the given electric field. Looking at the diagram, you can let the red dots represent a equal potential. The green lines are the results of vector addition. They are not impacted by the vector addition. However, the interior lines are, which is why they are straight lines. The first-hand investigation. On the left-hand side, you can see power pack, multimeter, and positive plate. On the right-hand side, you can see the negative plate, and between them, that grid surface is the conducting paper. This zoomed-in picture shows the gap on our grid. This is to make sure that we are measuring from the same point to minimize errors. In our experiment, the desired voltages flow through the conductive paper. For example, voltages that we measured were half a volt, 1 volt, 1.5, all the way up to 4 volts. Voltages are measured through the multimeter, as seen on the left. These points are pressed by the probes onto the carbon paper. The given equipotential lines are then plotted onto the A4 paper ready for measurement. This is a quick time lapse of the experiment. As you can see, we're using the multimeter to find whatever voltage we're looking for. Then once we've found it, we're going across the grid in order to mark that out on the paper. Results. In relation to our equations, E represents the strength of the electric field, V is voltage, D is displacement. As E depends on V divided by D, it can be said to be directly proportional. With this, a graph of the two would produce a linear line. This is a zoomed-in picture of our table that produces a graph. On the top left, you can see our voltage setting, for example 3 volts. Below that is the voltage that we were looking for. Next to that is our position in centimeters. And then on the right hand side is the magnitude of the electric field given by E equals V over D, which is our gradient. The units of this is newtons per coulomb. At the bottom of that column, there's an average gradient. You can get a general idea of how linear the line is going to be by how uniform the space between the lines are. The closer the lines are to being uniform, the more linear the line will be. This is our 3 volt setting. With the voltages, they were measured directly from the power pack with the multimeter, so they're not exactly what was presented on the setting. For example, this was 2 volts, but we recorded 3 volts. As you can see, the graph is fairly linear. The same is true for 4.5 volts. Graph is again linear. 6.6 volts, the space between the lines is fairly equal, so we should expect a linear graph. This is 8.6 volts. It's the same case, a fairly linear graph. this is 10.7 volts. Now as you can see with the white arrow, there is a large space in the middle of the map. So you would expect a different graph that would not be linear. When you see this shape is not linear at all, which means there was an error in our experiment. Why? A possible explanation for the anomalous results is the positioning of the paper. Fields are affected by the shape of the paper. Therefore, if we have paper positioned like the bottom left, it can distort the shape of the field, adding different dimensions of work as opposed to the simple x-axis of a plane. Application in technology: the electrocardiogram. The heart. In a heartbeat, a positive charge, a depolarization wave, travels from the heart across the body. The heart maintains its rhythm with electrical signals, as the movement of electrical signals causes the chambers of the heart to either contract or relax. The electrocardiogram. Due to the thoracic region and the axis of the heart, technology can be used to monitor field lines through the detection of equipotential lines. When a person has a heart attack, the movement of these electrical signals may be disturbed. An artificial pacemaker and a defibrillator can be used to initiate the rhythm of these electrical signals. Small metal discs, called electrodes, are placed on your skin. The electrodes are used to pick up the electrical impulses of the heart. The impulses are recorded, giving doctors a record of your heart's electrical activity. The diagram on the right shows the sites of electrodes across the body. Source analysis. Source 1. The Bozeman Science video. This source is moderately reliable, as Mr. Anderson has over 20 years teaching experience, and the given YouTube channel contains hundreds of videos with over 800,000 subscribers. One downside of this source is that it's developed according to the American syllabus, which differs slightly to that of Australia. More examples towards the end of the video may also increase understanding of electric fields. As you can see on the left picture, the video makes great use of illustrations in order to communicate the theory. In the middle picture, a screenshot of the demonstration of the field of positive and negative points, with the analogy of contour lines to explain that it requires no work to travel along an equipotential line. On the right picture you can see the specific example of two charged plates. An explanation is given describing the flow between the plates as the same as an object rolling down a slope. Source 2. The PhET simulation. PhET is an extremely reliable source of scientific information, as it's founded by the American psychiatrist Carl Wyman in cooperation with the University of Colorado. In this simulation on the main picture, you can see it allows for multiple tools to be used to see the connections between voltage potentials and an electric field. This source could be improved by having options to display equipotential lines as well as field lines instead of the arrows option, which is not as clear in displaying data on initial viewing. When zoomed in, it becomes apparent that most readings are more accurate at the center of the plates, as indicated by the relatively straight arrow. The curvature towards the edges of the conducting paper is also illustrated by the curved arrows towards the edges of the plates. Source 3. The Hyperphysics website. Hyperphysics is a reliable source as it is developed and published by Georgia State University. Hyperphysics provides the same example as the experiment conducted, that being of the constant electric field between two charged plates. Hyperphysics also supplies the critical statement, quote, "Electric field lines are perpendicular to the plates and the equipotential lines are parallel to the plates." The Hyperphysics website could be improved by adding further examples rather than just 3. It could also make further use of illustrations to explain more difficult concepts. Source 4. The Pressbook Report. Pressbook is a moderately reliable source with multiple publications as well as authors. Pressbook as a source can be improved by referencing the related equations as well as giving an explanation on the attraction between opposite charges. The source should also explain vector addition in order to explain the behavior of field lines. Image 1 is useful. As you can see, Image 1 demonstrates the behavior of electric fields and the position of equipotential lines. In Image 2, it outlines the shape of potential lines with 2 Q+ points. Note that the curvature of repulsion is a result of the addition of vectors, hence why they never meet. Source 5. Field force potential simulation. This simulation places a fixed charge and then demonstrates the field line and equipotential lines. You can then drop an electric field, either positive or negative, and observe the effects. The field force potential simulation also allows you to progress time and demonstrates the attractive force between the positive and negative charges. This simulation could be improved by allowing more than one fixed positive point. By allowing multiple points, you can simulate the experiment conducted completely. This is a bibliography in order as used in this PowerPoint. Thank you very much for watching. Hope you learned something.